The first thing that we will discuss is the abstract of the study. The silicon dioxide shell was coated on ferrous ferric oxide nanoparticle by hydrolyzation of sodium silicate. Hydrolyzation is a chemical reaction of a compound with water, usually resulting in the formation of one or more new compounds. And then, thiol groups were modified on the ferrous ferric oxide at silicon dioxide through siliconization reaction to form Fe3O4 at SiO2 SH sorbents. Siliconization is the covering of a surface through self-assembly with organofunctional alkoxysilane molecules. Mineral components like mica, glass, and metal oxide surfaces can all be silanized because they contain hydroxyl groups which attacks and displace the oxy groups on the silane, thus forming a covalent SiO-Si. Characterization with transmission electron microscope, energy dispersive spectroscope, and X-ray photoelectron spectroscopy proved that silicon dioxide and thiol groups were successfully covered on the surface of ferrous ferric oxide nanoparticle. The ferrous oxide nanoparticle is a core possessor for paramagnetism for magnetic separation, and the silicon dioxide shell could protect the Fe3O4 core from being oxidized or dissolved under acid solution and provide good modificability. Due to the strong interaction between mercury and thiol groups, the synthesized sorbents exhibited high adsorption capacity and good anti-interference ability during mercury adsorption. The maximum adsorption capacity calculated from Lamois fitting was 148.8 mg per gram at pH 6.5, and the sorbents still maintain good adsorption ability at low solution pH and high concentration of coexisting cations. Mercury loaded on the sorbents could be easily dissolved with 1 mole per liter hydrochloric acid containing 3 weight percent of thiourea, and the sorbent showed good reusability. The adsorption capacities were still kept over 110 mg per gram in tested natural water samples, showing practical significance in remediation of mercury-contaminated actual water. Introduction of the study. Mercury. Mercury is a high toxic pollutant that can be found in the atmosphere, natural water, soil, and food. Coal combustion, chlor-alkali industry, plastic industry, electronic industry, non-ferrous metal smelting, cement production, and mercury mining are some of the resources or sources of mercury pollution. Polluted water because of mercury can cause harm to human health. Neurodegenerative diseases such as amyotrophic lateral sclerosis, Alzheimer's, and Parkinson's disease. It can also damage the immune and cardiovascular and nervous system. Mercury is known as one of the priority hazardous substances by the Agency for Toxic Substances and Disease Registry. Various methods have been developed in order to eliminate heavy metals in polluted water. Absorption is recognized as the most effective and economic method for heavy metal removal. Recently, the application of nanomaterials in environmental remediation and pollutant removal became a focus due to their excellent properties such as high surface area, good adsorption property, and special photoelectric properties. Magnetic nanomaterials possesses super paramagnetism and can be readily separated from solution with an external magnetic field, showing great potential for heavy metal removal from environmental water. Although these magnetic nanomaterials have their own advantages, there are still disadvantages such as excessively complex preparation procedure, expensive reagents, poor stability, and reusability. It is high in demand to develop novel magnetic nanomaterial sorbents with simple preparation process, low price, high efficiency, good stability, and reusability for mercury removal. Magnetic nanoparticles are coated with silica shell to protect it from deoxidizing and dissolve under low pH conditions. The functional group can be bonded to silica shell solidly and tightly through a simple siliconization method. According to Pearson's hard-soft acid-base theory, mercury is classified as soft acid, which forms very strong bonds with soft Lewis base groups such as Cn, Rs, and Sh. A siliconizing reagent that contains a soft base group with silica-coated nanoparticle ferrous ferric oxide is expected to have a robust, stable, efficient, and super paramagnetic sorbents for mercury removal. 3-mercaptopropyl trimethoxysilane, a common reagent, was chosen to modify ferrous ferric oxide at silicon dioxide to get a novel mercaptopropyl functionalized sorbents for mercury removal from solution. Ferrous ferric oxide at silicon dioxide thiol sorbents characterize with several instruments and investigate the adsorption and desorption behaviors of mercury in them. The next thing that I will discuss is the experimental part of the study. Ferrous ferric oxide nanoparticles were prepared with a chemical coprecipitation method, and silicon dioxide was coated on ferrous ferric oxide nanoparticles through sodium silicate hydrolyzed under acid condition. First, 2 grams of iron 2 chloride tetrahydrate, 5.2 grams of iron 3 hexahydrate, and 0.85 ml concentrated hydrochloric acid were dissolved into 25 ml pure water to get solution. Sodium hydroxide was dissolved into 250 ml pure water to prepare 1.5 moles per liter solution. And then, the NaOH solution was heated to 350 Kelvin. Solution A was added dropwise into sodium hydroxide solution under nitrogen purging and vigorous stirring. The resulted ferrous ferric oxide nanoparticles were separated from the solution by a powerful NdFeB magnet and rinsed with pure water for 3 times. The ferrous ferric oxide were dispersed into 200 ml pure water, and the suspension was heated to 353 Kelvin under N2 protection and vigorous stirring. Then, 40 milliliters of 1 mole per liter sodium silicate was dropped into the suspension, followed by 2 moles per liter hydrochloric solution was added slowly into the mixture until the pH of the solution was adjusted to 6 within 2 hours. After the hydrochloric addition, the mixture was aged for 3 hours. The ferrous ferric oxide and silicon dioxide nanoparticles were washed thoroughly with pure water under the help of magnetic separation. The synthesized ferrous ferric oxide and silicon dioxide nanoparticles were activated in 100 ml hydrochloric solution for 12 hours, followed by washing with pure water to neutral pH. It was rinsed with 50 ml of ethanol and subsequently with 20 ml of anhydrous toluene, then dispersed into 100 ml of anhydrous toluene. The suspension was transferred in a flask, and the 10 ml of 3-MTTS and several grains of zeolite were added. The mixture was heated to microboiling and kept for 24 hours under reflux. After reaction, the resulted ferrous ferric oxide at silicon dioxide thiol nanoparticles were separated with the magnet and washed with toluene, ethanol, and pure water successively. Finally, the ferrous ferric oxide at silicon dioxide thiol sorbents were dispersed in 115 ml pure water to get 50 mg per ml suspension. Last na to, pre. The whole preparation procedure and the interaction between the sorbents and mercury can be seen in this figure. First, the ferrous ferric oxide was prepared and silicon dioxide was coated on it through sodium silicate or NaSiO3. As you can see, sodium dioxide was combined with the ferrous ferric oxide. Then, the suspension was transferred in a flask, and 10 ml of 3-MTTS and several grains were added. That's why ferrous ferric oxide at silicon dioxide thiol was made. Finally, mercury, because of the soft interaction of mercury in the thiol group, mercury also combined with the ferrous ferric oxide. That's why it became ferrous ferric oxide and silicon dioxide thiol with mercury combined with it. Characterization of sorbents. The morphology and particle size analysis were carried out on a transmission electron microscope of H7500 with an acceleration voltage of 80 kV after dropping the nanoparticles onto copper grids. Polytransform infrared or FTIR spectra were taken in potassium bromide pressed pellets on a Nexus 670 FTIR spectrometer. Magnetic property of the sorbents was analyzed using a vibrating sample magnetometer, and the binding energy and atomic ratio on the sorbent surface were analyzed using X-ray photoelectron spectroscopy. Next is the batch adsorption experiments. Mercury adsorption experiments were performed in 100 ml polypropylene bottles containing 50 ml aqueous solution. The concentration of sorbent was kept at 0.2 grams per liter, and ionic strength was adjusted to 50 milligrams per liter with sodium chloride stock solution. Effect of solution pH on the adsorption of mercury was investigated in the range of 3 to 7. Adsorption isotherms were obtained by varying initial mercury concentration 5 to 100 milligrams per liter. Adsorption kinetic study was carried out to take sample at the interval time of 5, 10, 20 up to 480 minutes. Potassium, sodium, and calcium were added into the solution to test the effects of coexisting cations on mercury adsorption. After absorption, the bottle was placed on a magnet for 5 minutes to separate the sorbents from aqueous solution. If the concentration of mercury was below 1 milligrams per liter, it was determined with an AFS 920 hydride generation atomic fluorescence spectrophotometer instrument and hydrochloric acid solution. Hydrochloric acid solution containing thiourea was used to desorb mercury. After adsorption of mercury, the sorbents were separated and mixed with desorption solution and the suspension was shaken for 2 hours. Then the sorbents were separated with a magnet, and the concentration of mercury in the supernatant was determined, which was applied to calculate desorption efficiency. Lastly is the sample collection. All natural water samples were obtained from different districts of Yantai, Shandong province. Tap water sample was taken from our lab in Zifu district, and surface water sample was collected from a lake in our campus. Seawater sample was acquired from coastal waters in the Yellow Sea. All samples were collected randomly and filtered to remove suspended particles.
We are now at the results and discussion part of the study. First is the characterization of ferrous ferric oxide. Ferrous ferric oxide encapsulated with silicon dioxide and ferrous ferric oxide modified with 3-MPTS. Looking at the first picture, it was revealed that before the microencapsulation of ferrous ferric oxide, its particles were multidispersed and had irregular shape with average diameter of about 10 nanometer. Second picture showed that after encapsulation with silicon dioxide, particles showed tendency to aggregate to larger ones. We can clearly observe that the dark nanoparticle ferrous oxide inside the silicon dioxide matrix. Silicon dioxide or silicate was used as the shell material to coat the magnetic nanoparticle or the ferrous ferric oxide from being oxidized or dissolved under low pH. Silica shells owns reliable chemical stability, biocompatibility, and versatility in surface modification. While at the third TEM image, white parts of the particles had become bigger, but still there is no obvious change occurred during modification with 3-mercaptopropyl trimethoxysilane. In this figure, we can see the graph of S3000N or energy dispersive spectroscope. We can see the ferrous ferric oxide gave only peaks for iron and oxygen. This peak. In this slide, after treatment with silicon dioxide, a strong peak of silica appeared in this figure, and Fe peaks were reduced. Next, for the EDS spectra after modification with 3-MPTS, obvious sulfur peak was observed, illustrating that 3-MPTS was successfully modified onto the surface of the material. Also, for the characterization of the compounds, XPS was applied to investigate the chemical elements on the surface of the sorbent. FTIR was employed to examine the surface groups of the synthesized materials. Zeta potential of suspension under varying pH was determined to investigate the PZC of these nanoparticles. The hysteresis loops were measured with a BSM to investigate the magnetic property of the sorbents. In this figure of wide-scan XPS spectra for ferrous oxide, silica-coated ferrous ferric oxide in red, and ferrous ferric oxide modified with 3-MPTS in blue, we can see that element Fe or iron, oxygen, and carbon were clearly detected on the surface of pure ferrous ferric oxide. While after encapsulation, this red line, we found that ferrous band were almost disappeared. Now we can see peak of silicon 2P and 2S at this point. This suggests that ferrous oxide core was completely covered with silica shell. Then, after modification with 3-MPTS, peak at the sulfur was observed and peaks at the silicon were disappeared. The result really agreed well with the one we first discussed on EDS analysis of the sorbent. Now, in this figure 3B, we can see broadband at 580 and 340, 3400 wave number. These bands indicate Fe oxygen, while these bands indicate OH stretching mode. And we can see decrease in FeO band for these two. The after encapsulation of silicon dioxide and after modification of 3-MPTS. A broad strong band at around 1100 wave number for both ferrous ferric oxide encapsulated with silicon dioxide and ferrous ferric oxide modified with 3-MPTS. These bands correspond to oxygen-silicon stretching. These small bands at about 2850 and 2900 wave number attribute to the CH stretch of methylenes of the alkyl chain from 3-MPTS, and again it shows that 3-MPTS was successfully grafted through the surface. If you are looking for the bands corresponding to the thiol group in these two, blue and red, it cannot clearly observe due to relative low content of thiol and poor sensitivity of IR to this functional group. In this graph of zeta potential of suspension under varying pH, it was found out that ferrous ferric oxide was found to be around 8.2. After encapsulation with silicon dioxide, the PZC decreased to about 3, which was consistent with pure silicon dioxide, indicating ferrous ferric oxide nanoparticles were fully covered with silicon dioxide. The PZC of ferrous ferric oxide encapsulated with silicon dioxide and modified with 3-MPTS was found at pH below 2, and the value was similar to 2,3-dimercaptosuccinic acid functionalized ferrous ferric oxide, which can be expected since their surface were both covered with thiol groups. To further specify whether ferrous ferric oxide nanoparticles were fully protected with silica shell, these three materials were immersed into 1 mole per liter HCl solution for about 24 hours. Ferrous ferric oxide was completely dissolved to form yellow solution, while no iron ions were detected in the supernatant of ferrous ferric oxide encapsulated with silicon dioxide and modified with 3-MPTS suspension. The hysteresis loops were measured with a BSM to investigate the magnetic property of the sorbent. As shown in this figure, no hysteresis was observed in the hysteresis loops of three materials, and the remanence and coercivity were nearly zero, exhibiting typical superparamagnetic behavior. The maximal saturation magnetization of ferrous ferric oxide encapsulated with silicate and ferrous ferric oxide modified with 3-MPTS were 55.05, 25.45, and 20.47 EMU per gram, respectively, calculated from the decrease of saturation magnetization. The introduced non-magnetic silicon dioxide was about 53.77 weight per percent. The modified groups were about 19.47% weight, and the content of sulfur was 4.15% weight, due to the ratio of it in the groups around 29.19 weight percent, which was a little higher than EDS analysis. The deviation might result from the decrease of saturation magnetization was not only from non-magnetic groups but also from oxidation of magnetic core during silanization. The sorbents could be separated from solution with a magnet easily and rapidly as soon as the magnet was taken due to the superparamagnetic property and largely saturation magnetization, which facilitated collection, regeneration, and reutilization of the solvents. Now, we will discuss about the effect of solution pH and interfering cation on mercury absorption. To investigate effect of pH on mercury absorption, the initial solution pH was adjusted in the range of 3 to 7 with mercury concentration of 40, 60, and 80 milligrams per liter, respectively. Three cations including potassium, sodium, and calcium cation commonly abounding in natural water were selected to investigate the effect of coexisting cations on mercury absorption on ferrous ferric oxide sorbents, and their nitrates were added to the solution before sorbents addition. To investigate effect of pH on mercury absorption, the initial solution pH was adjusted in the range of 3 to 7 pH, with mercury concentration of 40, 60, and 80 milligrams per liter, respectively. As shown in the figure 4a, with the decrease of solution pH, there was a slight reduction of absorption capacity, which might be attributed to competitive adsorption with the hydrogen ions at the lower pH condition. But unlike the sharp decrease on mercury absorption on bare ferrous ferric oxide and dimercaptosuccinic acid functionalized ferrous ferric oxide, the ferrous ferric oxide encapsulated with silicon dioxide modified with 3-MPTS still exhibit high absorption capacity for mercury over 90 milligrams per grams at pH about 3. Two factors accounted for the results. Firstly, the pZc of the sorbent was below 2 as shown in the figure 3c, and the negative charge surface of the sorbent at pH 3 facilitated to contact with mercury. Secondly, although competitive adsorption of hydrogen ion at low pH exists, the affinity between mercury and sorbent was higher than between hydrogen ion and sorbent. So the ferrous-ferric encapsulated with silicon dioxide and modified with 3-MPTS sorbents were suitable for mercury removal not only for neutral solution but also for low pH. Three cations including potassium, sodium, and calcium-2 commonly abounding in natural water were selected to investigate the effect of coexisting cations on mercury adsorption on ferrous ferric oxide encapsulated with silicon dioxide and modified with 3-MPTS sorbents, and their nitrates were added to the solution before sorbent addition. In this figure, a rapid decrease in absorption capacity was observed when concentration of cations enhanced from 0 to 50 milligrams per liter, then followed by gradual decline from 50 to 1000 milligrams per liter. When the concentration of cations were at 1000 milligrams per liter, the absorption capacity is still retained above 110 milligrams per grams, indicating that ferrous ferric oxide modified with 3-FPTS sorbent could selectively absorb mercury from complex matrix. And according to hard-soft acid-base theory, the Thiol group as a Lewis base, soft Lewis base, was more favorable to undergo remarkable interaction with soft Lewis acid mercury, rather than hard Lewis acid such as alkali and alkaline earth metal, potassium, sodium, and calcium-2 Besides the strong metal-sulfur interaction, the weak non-specific electrostatic interaction between sorbent and metal ions should not be neglected. When there was no coexisting ion, these two interactions resulted in the high absorption capacity for mercury. With the addition of coexisting cations, the electrostatic interaction between sorbent and mercury was destroyed. Thus, the absorption capacity decreased in the first stage. However, coexisting cations as hard Lewis acids could not affect the specific interaction between mercury and sulfur, so it was understandable that no obvious decrease for absorption capacity was observed with further addition of coexisting cations. Now, we are going to discuss about the adsorption isotherms of the study. Adsorption isotherm was carried out by varying initial concentration of mercury from 5 mg per liter to 100 mg per liter at 300 Kelvin and pH at 6.5. The absorption data of mercury on ferrous ferric oxide encapsulated with silicon dioxide and modified with 3-MPTS were analyzed with Langmuir and Friedrich isotherm models, and their equations were shown below. Where QE milligrams per grams and CE milligrams per liter were the equilibrium absorption capacity and the equilibrium concentration. H was the maximum absorption capacity and B was the equilibrium absorption constant. The maximum absorption capacity H could be calculated from the slope of the linear plot of CE over QE versus CE. Kf and N were the Freundlich constants The value of N and Kf could be obtained from slope of linear plot of log QE versus log CE. This slide shows the adsorption isotherm of mercury on ferrous ferric oxide, ferrous oxide at silicon dioxide, and ferrous ferric oxide at silicon dioxide modified with 3 MPTS. The absorption capacity of mercury on ferrous ferric oxide was below 20 milligrams per grams. This black. And almost no absorption of mercury was observed on ferrous ferric oxide encapsulated with silicon dioxide. And as for ferrous ferric oxide encapsulated with silicon dioxide and modified with 3 MPTS, Thiol, the absorption capacity was increased sharply in the first stage, with initial concentrations of mercury increasing, and then attained a platform. The results indicated that hydroxyl groups on the surface of ferrous ferric oxide and ferrous ferric oxide at silicon dioxide as hard Lewis base had no special interaction with mercury. The high absorption capacity for mercury on ferrous ferric oxide modified with 3 MPTS attributed to the strong special interaction between the surface thiol group, soft base, and mercury and soft acid. The absorption data of mercury and ferrous oxide modified with 3 MPTS were analyzed with Langmuir and Freundlich isotherm. In this table, we can see the Langmuir and Freundlich isotherms parameter for mercury absorption on ferrous ferric oxide encapsulated with silicon dioxide and modified with thiol, or 3 MPTS. The fitting parameters of these two models were shown in this table. The correlation coefficients, or R-squared, for Langmuir and Freundlich model were 0.996 and 0.849, respectively. The good agreement between the absorption data in Langmuir model implies that the absorption of mercury on ferrous oxide at silicon dioxide modified with 3 MPTS occurred as a single monolayer. The maximum adsorption capacity of mercury on ferrous oxide modified with 3 MPTS calculated from Langmuir adsorption isotherm was 148.8 milligrams per grams, which was higher than Fe3O4 of 97.7 milligrams at pH 6, and Thiol HSM 140.1 milligrams per gram sorbents, and was comparable to DMSA ferrous oxide with 227 milligrams per grams at pH 8.1. The ferrous ferric oxide modified with 3 MPTS sorbents showed excellent capability for mercury removal. We are now going to discuss about the adsorption kinetics of the study. The kinetics of mercury absorption on ferrous oxide encapsulated with silicon dioxide and modified with 3 MPTS was performed by contacting with 60 mg per liter of mercury solution at pH 6. Pseudo second order kinetic model was applied to describe the absorption of mercury on ferrous ferric oxides encapsulated with silicon dioxide and modified with 3 MPTS, and the linear model was shown below. T over Qt is equal to 1 over KQE squared plus 1 over QE T, where K is the rate constant of absorption, G per mg minute. Qt is the absorption amount of mercury at any time, mg per gram. Q is the equilibrium absorption capacity of mg per gram, and the initial absorption rate H mg per gram minute can be defined as H is equal to KQE squared as time approaches 0. Both K and H can be determined experimentally from the slope and intercept of plot of T over Qt versus T. The pseudo-second order kinetic model fit adsorption data well with R squared over 0.998. The constant K and H obtained from the slope and intercept of plots are presented in Table 2. In Figure 6, it shows that the uptake rate of mercury at temperature of 293 and 303 Kelvin, the absorption capacity was enhanced rapidly in initial time, as you can see in the graph, and then slowed down and reached equilibrium. Finally, at 303 Kelvin, 1 hour was enough to attain absorption equilibrium, while 4 hours was required at 293 Kelvin, indicating that high temperature was in favor of adsorption. The fast absorption should attribute to the readily accessible of mercury to the binding sites, which were coated on the exterior surface of the sorbents. The equilibrium absorption capacity at 303 Kelvin was higher, about 5 mg per gram, than at 293 Kelvin, indicating that absorption was endothermic reaction. In this table of pseudo-second order rate constant for mercury adsorption of ferrous ferric oxide at silicon dioxide modified with 3 mpts, higher temperature of 303 Kelvin produces higher R squared of 0.999. Now we are going to discuss is about desorption and reusability of our material. To achieve the recycle of sorbents, the mercury loaded on the sorbents should be desorbed efficiently without damaging the structure of the sorbents. Nitric acid and hydrochloric acid were reported to desorb mercury from mercaptopropyl modified silica matrix sorbents. Nitric acid might destroy the mercapto groups due to its strong oxidizing property. Different concentration of hydrochloric acid, 10 ml, was applied to desorb mercury after the sorbent was separated from solution with a magnet and the supernatant was decanted. The results showed that over 98% of adsorbed mercury could be desorbed with 6 mol per liter HCl, but desorption solution presented obvious color of ferric ion, suggesting part of the iron core was dissolved in strong acid. To improve the desorption efficiency, thiourea was introduced into the desorption solution. Mercury absorbed on the sorbent was desorbed with desorption solution, and the sorbents were collected and rinsed with pure water thoroughly for reuse. 10 milliliters of HCl, both 1 molar and 2 molar, containing different content of thiourea, was mixed with the sorbents for mercury absorption, and the results were shown in this figure. About only 30 and 40% mercury was desorbed with 1 and 2 mol per liter HCl without thiourea, and the desorption efficiency enhanced obviously with addition of thiourea. The adsorbed mercury could be fully desorbed with 1 mol per liter HCl containing 3% of thiourea, or 2 mol per liter HCl containing 2% per weight of thiourea. Since no iron was leached when the sorbents were immersed in 1 mol per liter HCl for 24 hours, 1 mol per liter HCl containing 3% weight of thiourea was selected as desorption solution in the next experiments. In this graph, we can see the absorption capacity was 130 milligrams per grams in the first use of sorbent and it decreased to about 105 to 95 milligrams per grams in the second and third use. In the subsequent two times of reuse, the absorption capacity kept almost stable. The decrease of the absorption capacity in the first two reuse might result from the loss of part mercapto groups which were not bonded to silica surface tightly in the desorption process. The remnant mercapto groups were bonded to silica surface tightly and not readily to be destroyed by desorption solution. Thus, the absorption capacity remained stable in the following reuse. The absorption capacity was still over 90 milligrams per grams after 5 times of recycle, suggesting excellent reusability of the sorbents. Last is about the discussion of adsorption mechanism and environmental significance of our sorbent. The ferrous oxide, encapsulated with silicon dioxide and modified with 3-MPTS loaded with mercury, was characterized with EDS and XPS to discuss the absorption mechanism. The potential application of ferrous oxide, encapsulated with silicon dioxide and modified with 3-MPTS for removal of mercury from natural water was tested by carrying out absorption equilibrium isotherm using tap water, lake water, and seawater as a matrix. The equilibrium absorption data and the feeding parameters for Langmuir and Freundlich models were shown in Figure 9 and Table 1 respectively. This EDS spectrum in this figure showed that the sulfur peak is split into two peaks of sulfur and mercury, indicating mercury was absorbed onto the sorbent. While in this spectrum, the mercury peaks appeared in the wide-scan XPS spectrum, which was in accordance with the EDS analysis. The binding energy of the narrow XPS spectrum for S2P was 163.8 electron volts, corresponding to the RSH group. After absorption of mercury, the binding energy of S2P shifted to a little higher value, which might result from the donation of the electrons from S atoms of thiol groups to mercury. This figure presented the narrow spectrum of Hg4F. The binding energy revealed a single peak around 103.6 electron volts, which indicated that mercury was absorbed through the chelating binding between the mercury and sulfur. The studies on the absorption of mercury on ferrous oxide encapsulated at silicon dioxide and modified with 3-MPTS showed the participation of sulfur in complexation with heavy metal through XPS spectra analysis. This graph shows that due to the competing absorption of interfering substance, the absorption capacity in natural water matrix showed decrease in certain extent. Nonetheless, the absorption capacity was over 110 milligrams per grams in all tested water samples, showing excellent performance in mercury absorption from natural water. After treatment by 0.2 grams per liter of sorbents, the residual mercury in the natural water samples spiked with 5 milligrams per liter mercury was under the limit of detection of HGAFS, and it was below 10 micrograms per liter in one spike with 10 milligrams per liter mercury. Taking into account the high absorption capacity and the low amount of residual mercury, The ferrous ferric oxide encapsulated in silicon dioxide and modified with 3-MPTS was a promising sorbent to treat mercury-contaminated water.